I will give you a brief introduction to the subject, very interesting subject. There are no way I'm going to go into any details, but I'm sure those two gentlemen will do something about that after the presentation. If you look upon the thesis, I have 4 images or figures on the front cover of the thesis, which is actually the 4 pillars of the work here. This is a figure showing that the CO2 level in the atmosphere has been increasing over the last 50 years. We have to do something about that, so people have started firing biomass in this country, straw for most of the part. The problem with the straw is that there is a risk of forming deposits on superheater tubes, and this will cause a low electrical efficiency, so we have to do something in order to solve that problem and increase the electrical efficiency of this. As I said, the CO2 level in the atmosphere has increased over the last 50 years from about 350 ppm to 385 ppm. As a consequence of this, there are different numbers of climate models that predict an increase in the temperature somewhere between 1.1 and 6.4 degrees centigrade over the 21st century is predicted. Now this has some consequences, one of them being that this beautiful creature will end up like this. We don't want that to happen for sure, but of course there are also other more serious problems with this. Rising sea levels, I mean, if you live in Florida, South Florida, you should be aware of this. There are problems, potential problems with increase in the intensity of extreme weather events. We have probably already seen some of these things here. There are probably some changes in the pattern of precipitation. There may be a decrease in the agricultural yield as a consequence of this. There may be modification of trade routes, and then we have seen already some significant glacier retreats going on. So we have to do something about this CO2 level in the atmosphere. What can we do? If we look upon the carbon cycles of different fuels, over here we have the biomass. The time from the point where we emit a certain amount of CO2 from biomass combustion and until that CO2 is recaptured is in the order of years, maybe down to a year, a single year. If we take the same situation for coal, the time from the point where some plant material captures some CO2 and until you have a coal seam, this is done under the influence of pressure and heat over a very long time, up to millions of years. So the recapturing time and the regeneration time for coal is a lot longer than it is for biomass, and this is the reason why somebody came up with the idea that we can decrease the level of CO2 by burning biomass. Everything comes at a price, thereby also the combustion of biomass. Here I have shown a Van Crevelen diagram which shows the content of hydrogen and oxygen versus carbon in different fuels. In here we have the old fuels, the fossil fuels. They have a low content of carbon, oxygen and hydrogen, but out here we have the biomasses. These fuels have a high content of oxygen and a high content of hydrogen. Some of the oxygen is present as carboxylic acid groups, which has a counter ion, typically either potassium, sodium, calcium, or maybe even magnesium. And these counter ions have a tendency of leaving the system. They are released to the gas phase during combustion. In this case, you can see release profiles for a number of different annual biomasses for potassium, and you can see that at the highest temperature we have a release of somewhere between 60 to 80% of the potassium. For the chlorine, all the chlorine is basically leaving the fuel during combustion. So we have a bad cocktail here, combination of potassium and chlorine. There's a lot of chemistry going on in these systems when we burn the biomass. All kinds of interactions between potassium, chlorine, and sulfur leading to SO2 levels and HCl level in the gas. And another important thing, formation of aerosols, small particles in the system. I'm sure we will have a discussion about this later on when we start the questioning part of this. Here is some data from one of the metering campaigns where you can see the mass loading of aerosols in a flue gas versus the concentration of potassium in the ingoing fuel, the ingoing straw material, and you can see that there is kind of a straight line between those two. Somebody's picked up these aerosols and had them analyzed chemically, and you can see that a lot of the material in these aerosols are actually either potassium, chlorine, and sulfur. Based on this, we had an aerosol technology group at the department some time ago that came up with this idea that the sulfation of KCl in the gas phase to potassium sulfate leads to formation of aerosols. And we will have a discussion about that later on also, I'm sure. The problem with the combination of potassium and chlorine is that it causes deposition in these boilers. And if you have a closer look upon the structure of those deposits, you will see that in the inner layer you have a very high concentration of potassium chlorine. This is a bad situation for the material that these tubes are made of. It can cause corrosion. I have another image here. This is an inner layer of one of the straw-fired plants we have here in Denmark. You see this inner layer, the only thing I find when I analyze it is potassium and chlorine. So we have analytically pure potassium chlorine in the inner layer. What happens if you have an inner layer sitting on a tube which is rich in potassium chlorine? Well, there's a risk of having a reaction with SO2 from the gas. This reaction may cause release of chlorine gas, which may penetrate through the oxide scale and react with either chromium or iron in the alloy material. This will form volatile chromium chloride or iron chloride, which will then move out through the oxide scale till it reaches an atmosphere with oxidizing conditions and be reoxidized to chromium oxide or iron oxide. So the presence of chlorine close to these superheater tubes causes some kind of an extraction of chromium and iron from these systems. What can we do about this? There are a number of different means we can apply in order to minimize this effect. One of them is to apply an additive, and we've been working on that for a while actually in connection to this. In principle, we have two different types of additives. The first one here is, the basic idea is that you inject an additive and you have some kind of unwanted compound removed from the gas by a chemical reaction on the surface. The other type of additive, the black guys here, the idea is that you have them actually to sit on in the same spot as the rest of the material that are deposited on the tubes, but these causes inhibition of the sintering, which means that it's fairly easy to blow this one off the tube. So we have in principle two different types of additives that we can apply. We have been working mostly with this one, where we have an interaction between some gas component transforming an unwanted gas component into something which is harmless in the system. Actually, if you look upon the sulfur to chlorine ratio in the fuel, it's very important for the total amount of chlorine in the deposits. So if you have a high sulfur to chlorine ratio in the fuel, you have a low chlorine level in the deposits. So actually by adding some kind of a sulfur-based additive, you should be able to ensure a low concentration of chlorine in your deposits. Here is an example from the Avedøre power station where they did aerosol measurements, collecting aerosols under different campaigns where they were adding different types of additives. And if we take the first figure here, the reference case, this is the pure straw firing case. And those two cases are cases where we have added some kind of a calcium phosphate additive. You see that the area below those two curves are smaller than the area below the reference curve, which means that when we put these additives into the system, we have a lower aerosol mass loading in the system. So by adding an additive, we get lower mass concentrations of aerosols. The same story goes for this sulfur-based additive. We tested some of these same additives as was tested in this full-scale plant in our entrained flow reactor, and saw that there's also an effect on the chlorine level in the deposits, at least when we see them in the entrained flow reactor. There's a lot of interesting chemistry going on with these additives, depending upon what type of additive we have. Is it aluminum silicon based? Is it phosphor based? Or is it sulfur based? The basic idea and the ideal additive would be one that remove an unwanted compound and transform it into some high melting species that will not cause deposition. And then we have, for example, chlorine released as a harmful lesser harmful species than was originally present in the system. But again, everything comes at a price, and adding an additive into the system can cost money, something you have to be aware of. Another angle of this work is the shedding work. We have been doing quite a lot of work on shedding actually. Shedding is the falling off of the pieces of deposits from a tube. If you look upon the deposition process, it's a cyclic process, meaning that first you build up a thin layer of something which makes the tube sticky. Then you have deposit of somewhat thicker layers of somewhat bigger particles. And then at a certain point, you have an accelerated growth of deposits because the tube is getting wet on the surface and it becomes easier to retain the particles upon impact. So it's a cyclic process, which means that from time to another, you have some of the deposit that has built up on these tubes to fall off. And then you build up a new layer. Actually, I had 10 years, a little more than 10 years ago, the pleasure of acting as chairman on a conference in the very same room as we are here. A totem meeting where we were addressing all kinds of ash-related issues. And one of the conclusions from that meeting were that we needed some more attention on shedding. I mean, people have been doing all kinds of work related to adhesion of particles and formation of different types of ash particles, but we needed some more focus on shedding. So we started out by making a huge review for the literature where we collected all the variable information. And then we developed a probe, a specially designed probe, which is where we are able to quantify the amount of deposit and the heat uptake at the same time, basically. So we can quantify how much heat is actually taken up and how much deposit is actually built up on this probe. We have tested the probe again at the power station where we plugged it in and did some measurements, and you can see some of the raw data here. You see the temperature profile, that's the gray one, and you see the mass of deposits being built up on the probe. You see it increases up to a certain point, then we have something to fall off the probe, and we have a new build-up on the other side of that one, and a fall off and a new build-up. If this is raw data, if you average them over certain time periods, you can get signals like this, and you can then start analyzing how long is the deposition and how long is the shedding time for that actual system and that actual fuel. Here is an example just to show you some images of what's going on there. Here you see the effect of the temperature on shedding in this system. We are looking in on a probe which is placed in the flue gas channel, and we are looking from this side below up against the south side of the probe. You see that at 930 we have an almost dry surface on the south side, which is coming in contact with the gas here. But if we increase the temperature, we start building up these droplets, and at 1100 we have seriously formed big droplets which is literally dripping off the probe. And this is what is happening. Most of what I've been saying until now have been dealing with straw-fired systems. We have done a number of full-scale measuring campaigns of some of the straw-fired systems. Haslev, for example, Rudkøbing is another one, Masnedø power station, and Maribo-Sakskøbing. We have also been there doing measurements of different kinds. We have done two types of measurements, basically. Probe deposits, which is typically a cold finger that you stop into the flue gas channel. These probes has a very short exposure time, and they are sort of an fingerprint chemistry you get out of these probes. You get an immediate feeling of what is going on chemically in the boiler. We've also been analyzing mature deposits, in-boiler deposits, which has been taken out from tubes inside the boiler. And these deposits have typically been sitting for thousands of hours, so they have a more mature chemistry. One of the examples is the Rudkøbing power station, and the conclusion, if we look upon the fly ash chemistry, lots of potassium, lots of chlorine, and the same story goes for the deposit chemistry. This story, the problem with the potassium and chlorine going together is that you may have this reaction with SO2 from the gas forming potassium sulfate and then releasing some chlorine gas close to the tube. And for that purpose, you have to keep the temperature fairly low in these plants in order to avoid serious corrosion. Therefore, you get a low electrical efficiency in these plants. Somebody came up with a good idea here now. If we look upon the electrical efficiency of other types of plants, coal-fired plants, for example, you see that over the years, the electrical efficiency has improved significantly. And for some of the coal-fired plants, we are at electrical efficiencies of, say, 46 to 48%. So if we are able to sneak in a little amount of straw into these systems, we get a much more efficient transformation of the straw. And that is the basic idea. So let me say a few words about the wonders of co-firing. This is an exciting world. First case was the Vestkraft power station in Esbjerg, where they blew in the straw in 2 tubes in the middle of the burner gallery. So those 2 tubes were surrounded by coal-fired boilers. And I believe that they saw at least one negative consequence, which is that the straw was blown directly across the furnace and burned up all along the wall here. Or there was a drop of knees from the straw structure, which burned out in the hopper of the system. So it kind of indicated that you can burn straw, but it's not a very efficient way of doing it like this. But then somebody came up with this idea, let's downscale this system to a single burner instead of an entire burner gallery. So the next good idea, we now introduce the straw in the middle of a burner and have a swirling coal flame surrounding the straw, which gives you a very tight contact between the coal ash and the straw, which is releasing potassium and chlorine. The good story here and the big chemical scoop of co-firing is the fact that you take care of most of the potassium from the straw ash by use of the coal ash. The coal ash is, so to say, working as a sort of an additive here, taking care of most of the potassium, while most of the chlorine is leaving as HCl, which is harmless compared to the other situation. We've also been involved in a number of full-scale metering campaigns on coal-fired systems over the years. One of them, a classical one, is the Studstrup power station in Midtjylland. Here we plugged in probes all the way from the top of the furnace down through the convective section of the boiler. We applied different metal surface temperatures and different exposure times all the way from 15 minutes up to about 72 hours for some of them to see if there's an effect also of the exposure time. The conclusion, and there's an outline in the thesis and there are a lot of papers behind that work. The conclusion, I believe, is that coal quality is pretty important. If you fire coal with a high quality, as is usually the case in the Dong area, you should be able to do this. You should be able to transform those 20% straw without any problems. But, and there's a big but here, if you take some low rank coal into account here, then you may have a problem. We were lucky enough to enter an EU funded project a couple of years after the Studstrup power station campaign, and some of the German participants in that campaign offered to fire a pretty nasty combination of brown coal, which is a low rank coal, with a Danish straw with a high content of chlorine and a high content of potassium in the RVE test facility in Germany. Now, if you look upon the extent of deposition in those 2 cases, without straw and with straw, it doesn't look as if there's a big difference here. But then if you try to remove those 2 deposits, you will find out that this one has a glassy structure. It's almost impossible to remove from the tube, while that one can be blown off rather easily. So there's a significant influence of the presence of straw. And the conclusion of the campaign we did down there at the RVE test facility is that you should not combine low quality coal with straw. Beware of that. We have also been involved in developing analytical work. There are a number of places where we have done some significant contributions here. Ash fusion test, for example, the melting of ashes. I'll show you that in just a second. We have contributed to the SEM-EDX analysis, or rather to the CC-SEM analysis of ashes. We have done a lot of viscosity work, actually. It's not mentioned in the thesis here. And then we have helped gaining results that can be used to test chemical fractionation in other places. Ash fusion. Those of you that work with fuel characterization know that this is a classical technique. You make an ash of your fuel, you produce a little conus, and you follow the shape of that conus as a function of temperature. You notify different temperatures where the conus has different shapes. The first one here being the initial deformation temperature. This is believed to be the point where you have the formation of the first little droplet of molten phase. We came up with another way of doing this, where we do the melt quantification by use of an STA. And in our system, you get a continuous curve so that you have a full line of melting going on as a function of temperature in the system. And if you compare our method, which is the blue one here, with the IDT for that same ash, you see that in our system, we predict that there's liquid in the system at a temperature which is 60 degrees lower than what is predicted by the classical Konus test. 60 degrees is not even the worst case. We have some other cases where we found differences of up to about 300 degrees centigrade between the point of formation of the first little amount of liquid in the STA compared to the Konus test. So that's an example of some of the work we have done on the ash melting and quantification stuff. We have also been contributing to the CC-SEM and SEM-PC work. Now, if you take a bulk ash and you make a chemical composition of that one, you have a single composition. In a diagram like this, you have one point, the blue point here, you have one composition. Every ash particles are assumed to have the same chemical composition. This is not the case in real life. In real life, you have particles that are size distributed and they have different chemistries. So we have to do something about this. Way back in the 80s in America, they came up with this idea that we could do CC-SEM analysis on this. In the CC-SEM analysis, you get a particle-to-particle analysis, which means that each and every one of the single particles have their own chemistry. From a modeling point of view and from an understanding point of view, this one makes life a lot easier than the bulk gas chemistry. The problem with this method is that it was developed in America a long time ago for coal-derived ashes. And we had this purpose of doing studies on ashes derived from straw, for example. So we made a development. The basic idea first. The basic idea is that you bombard a sample and you have different backscatter electrons and secondary electrons coming out of that, and you have an X-ray signal that you can use to analyze for the chemistry and the surface structure of the sample. But we made a development of the original coal chemical classification, which is shown here, and added the green one here, so that we are now able to do these types of analysis also for biomass-derived ashes. After that work, we have also done it for waste-derived ashes. And we are now in a process where we are trying to do the same thing for cement products. The last point I'm going to mention here before I wrap all this stuff up with a quick summary is that we have also set up an ash course, which is fairly important because it allows us to make training of new people coming into the system, and it allows us to accumulate information. Every time one of our students comes with something interesting, I accumulate it in the ash course material, and as you can see, we cover all the aspects, all the interesting aspects going on there. We have fuel and ash characterization, we have boiler technology aspects, we have ash and deposit formation, sintering, shedding, we have corrosion aspects, we have trace element chemistry going on. So it's an interesting and it's a very efficient way of accumulating information and making sure that we can at all time give a quick introduction of new people coming into the system, not only at our university, but also among some of our industry, some of the industries that we work together with. Let me make a wrap up of what we have obtained here now. What is it that we have achieved with this work and that I have described in the thesis here? Well, we have now a documentation for the research activities on different things. Straw firing. We have done a lot of release studies trying to quantify how much potassium, how much sulfur, how much chlorine is released from the straw as a function of time and other parameters. We have done some lab scale exposure of test elements to corrosive gases and analyzed them together with people from our good friends at the DTU Mechanical Engineering. We have done a lot of probe measurements. We have done additive studies, both in our entrained flow reactor, but also in big real life. And we have done shedding studies. We have also been involved in the cold straw co-firing. We have done probe measurements. We have done a study on the effect of coal quality on the pilots in pilot scale. We have developed, as I showed you, 2 examples of some analytical techniques like the ash melting and the CC-SEM classifications scheme. And I believe that we are ready now to take on the next step, which will be pure biomass firing in suspension, I believe. And we have an activity as part of a newly funded project called GREEN, where we will address that one in close cooperation with industry. We have also done a systemization of data. I have been involved in several national and international projects, and I've tried to systemize the data, make them variable for people. And then we have accumulated know-how to a significant degree. If we look upon the understanding of the process, the whole process of something coming into a furnace and then causing a deposit somewhere in the system, I believe that we are doing pretty well on most of it. There is a bit of a gap in the way we understand the formation of fly ash in store-fired systems. There we have to do some supplementary work if we want to understand that fully, especially addressing the particle size development and the chemistry of the fly ash particles. We are also doing pretty well on the shedding, at least on the cylindrical probes. We have done a lot of work in close cooperation with the industry on corrosion activities. We have studied additives. We have still people working on the poisoning, the probable poisoning of SCR catalysts in coal-fired systems. And that's about it. I've mentioned here or shown some logos for some of the funding agents. There are other institutions that are not shown, not because I'm a bad guy, but I didn't have space for that. And I didn't even try to come up with a list of all the people that I should say thank you to for contribution to this work. So I just put an image of a big group of people there. Thank you.